All right. So I tell you all of that about inductors and resistors and capacitors so that I could talk about impedance. Impedance. And the things we need to know here before we got that, in an AC circuit can be described by its components. By its components. So if it's purely resistive, which means it only has what?
Resistor.
Only has resistors, then you just say it's an R circuit, resistive. If it is purely capacitive, that means it only has capacitors, then we just say it's a C-type circuit. If it's purely inductive, then it means it only has inductors, then it's L. So if we combine that, we could say, well, if it's an RC circuit, then it must have resistors and capacitors. Or I could say it's an LC circuit, then it only has inductors and capacitors. Right? But if it's an RCL circuit, then it must have resistors, capacitors, and inductors. And that's why you'll see something called an RCL circuit. All right, but any circuit that is not purely resistive, means it has an inductor or a capacitor or both, must have total opposition to current flow, represented as impedance. I-M-P-E-D-A-N-C-E, represented by the letter Z. Impedance okay, so when we did circuits with DC, and we would do the circuit, and right next to the voltage source, the power source, we would always have E total, I total, and R total, right? And R total was the sum of the resistance, and there was nothing else to it, and that's just as complex as it actually gets. Now, in an AC circuit like this, we can still have E total, I total, and we can still have R total, but in this case, when I say R total, it's only the sum of the resistors. And so what about the inductors, which is inductive reactance expressed as ohms? Okay, so am I going to have R total, I total, R, L, and C totals? Well, no, I'm not. We can have an R total. We can definitely have inductive total, which is also called inductive reactance, or capacitive total, which is called capacitive reactance. But when you add up, I want to use the word add carefully. I don't mean add and plus. When you combine that, when you combine resistance and you combine inductive reactance and you combine capacitive reactance, you get impedance. That is the combination of them all. And it's not something you can simply just add up. Where am I? Impedance is not the sum of each. Impedance is not the sum. What does sum mean? The addition of them. It is not the sum, but a vector sum. Vector sum. And do you remember my friend vector?
Yes.
Vector is what?
Direction and both directional.
Is a quantity having both magnitude and direction. Oh yeah! Something like that. I don't know. All right. It's not the sum, but a vector sum. All right. Because. B-E-C-A-U. Because capacitors and inductors, so I could put, I'll do it the simple way, capacitors and inductors. Capacitors, remember, is X of C, and inductors is X of L, if we want to talk about the reactance. Because capacitors and inductors have opposite effects, what do I mean by opposite effects?
The phase shift.
Phase shift, Eli the Iceman. They're completely opposite. So in Eli the Iceman, Eli, I'll write it again, Eli the Iceman. So just like, and I'm still where's my soapbox? I'm still shocked. And I told you that when I do simple DC problems, simple ones, I teach the subject. I still put this on the top of my paper, EI and R. Watch me do. I'm not ashamed to do it. I still put EI and R when I'm doing one. Why? Because I want it there. I don't want to make a mistake in front of somebody. So I'm less embarrassed to put EI and R on a piece of paper. But a lot of you guys still won't do it. And I'm like, okay, so what is the resistance of that? And you're like, I don't know. It's like I divided by E. Really? Just write this down on your piece of paper. All right, so that's why I'm writing Eli the Iceman in front of me right now, rather than just go. I want to see it. And I want to tell you, as I tell you this, capacitors and inductors have opposite effects, that in an inductive circuit, the voltage leads the current, and in a capacitive circuit, say it with me, current leads the voltage. And I'm going to write it and actually look at it. Why? Because I'm not afraid to do it. I'd rather be, what's the saying? I'd rather be thought a fool than open my mouth and remove all doubt. So since I'm up here opening my mouth, I guess the secret's out of the bag. But hard to get the cat back in. But anyway, don't be ashamed to write cheats on your it's not cheating if you're just doing that, you know. So that's using your brain. Let me see. Where am I now before I got out? Impedance, not sum, but a vector sum, because we can use, because capacitors and inductors have opposite effects, meaning, and I explained that, opposite effects, comma, where'd I go? We can use algebra, to find total resistance. I don't know if I really want to write total resistance. I kind of want to scratch that out and put impedance. Well, no, actually, you know what? I know where I'm going with this. Let's just leave it at total resistance. Total resistance, and when I say total resistance, I'm going to say this, X of L / X of C. So it's not impedance yet. It's still total resistance in terms of X of L, X of C. So we find total resistance for CL circuit. What does that mean? And really, it's not algebra. It's almost simple math. So inductive reactance, so X of L will be positive. Now I put because it causes voltage to lead. So what the heck? Because it causes voltage to lead. And then capacitance, or X of C, make sure that's an L, X of C will be negative because it causes voltage to lag. Causes voltage to lag. So the formula then becomes X total. There's a new term, X total, and this is a formula that you're going to want to have on your sheet. Equals X of L plus negative X of C. Make sure your X of C is negative. So that's the same thing as saying X total equals X of L minus X of C.
So what's this formula for?
For finding X total. That's a new thing. What is X total? X, I'm glad you asked. Well, thank you for asking. So X total is the effect of the circuit when you consider X of L and X of C. So as I've mentioned several times, if we have an inductive circuit, what's it going to make the voltage do? There's everything amps.
One more time, can you point out it?
Right there. What happens in an inductive circuit? What happens to the voltage and the current?
Voltage leads the current.
Okay, so the current starts falling behind. Okay, current starts falling behind. And so over at SMUD, they got a guy sitting on a chair just like this. No, I can't talk bad about SMUD guys at all.
PG&E, they're under a lot.
They're in a lot of stress. But you know what? Some of those PG&E line pole guys are pretty rough. So they got a genius of a guy.
Why are you scared?
I know they're union, what are they, Teamsters? I don't know. So they got a cigarette, and he's in charge of the capacitors, right? And so he's got a bottle of scotch in one hand, a cup with a little ice, and it tinks. You like that sound? Anyway, every time, and he's got a meter, and it says, whoa, starting to get out of phase, so I better add what to the system? Capacitors. Adds a capacitor, and boom, nails it. We got our volts and our amps right in phase. And so, but if that's not the case, his union's got to go on a break, right? He's got to pee eventually. So he leaves, and at the same time, all the girls at my house turn on the hair dryers, and so what happens is it gets all out of phase. So if we look at that, we take, okay, well, how out of phase is it? Well, we have X of L, right, from all of the inductors that are online, minus the capacitors that were put online before Harold took a break. Got it?
So you know him personally?
Yeah, I do.
He has a cigar, by the way.
Yes. All right, so that will be X total. So now, wouldn't it be nice if X total was 0, then everything is in phase. But if it's not, and hair dryers and air conditioners took over, XT is going to be a positive number, and that means that it's going to be more of an inductive circuit, so we can look for voltage to lead. Now, turn it around, right? Harold took a sick day, and they hired a temp who, doesn't know what he's doing. And so before he goes on break, he just puts all of the capacitors online.
He's thinking ahead.
Thinking ahead. I was putting them, how many? All of them. So all the capacitors online. So we look at X of L, all the hair dryers and such that are going on, and air conditioners. But we have way too many capacitors. Then XT will be a positive or negative number. Be a negative number, which means that it's capacitive and current is going to lead. So that's how you're going to get X of T. You're going to look at this X of T. If the X of T is positive, you have inductive reactance. If X of T is negative, you have capacitive reactance. All right, and that's gonna be one of our puzzles that we have to deal with. It's a fun puzzle. Let me see. Okay, what about resistance? Where did that come in? Because resistance, R, does not have an effect on phase. I wrote here, it cannot just be added to reactance, but well, I can go with that. It cannot be added to reactance, which is X total. Right? It doesn't work that way. So how are we going to factor in resistance? Again, I'm glad you asked.
I thought you did.
So if we graph this out, this is what it's going to look like. On a graph, this will be x of L up here because it's a positive number. This will be x of C because it's a negative number. And along this line here will be resistance. So resistance is horizontal, inductance is going up, capacitance is going down, and what's the word we're working with here? Impedance, which is represented by Z. Impedance is going to be the hypotenuse. Impedance, which is Z, is the hypotenuse. H-Y-P-O-T-E. Hypotenuse. I might have spelled it close to it. So using this little chart right here, if I had some x of L and some x of C, I don't want to make up numbers right now, but I had more x of L than x of C, it's going to be an inductive or capacitive circuit. We can just make 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so if I had 10, x of L is 10, and x of C is 4, and resistance equals 8. All right, I just made up some numbers here. You got that? X of C. So what is xt? All right, x of t is 6. What is RT? 8 ohms. All right, everybody follow where I got those? Okay, I made this up just off the top of my head. I just said x of L is 10, x of C is 4, and resistance is 8. X total is what?
6 ohms.
Okay, where did 6 ohms come from?
10 minus 4.
Okay, it's 10 minus 4, right here. 10 minus 4. So 10 minus 4. So it's a positive 6. So it's a positive 6. I'm just making this up. 2, 4, 6. It goes right there in my line. Right here. Because each line I made is worth 2. Why is it worth 2? Because I just made that up, okay? So I made that up. Each one is worth 2, and I said our total is 8. So 2, 4, 6, 8. So that comes right there. And so Z now becomes the hypotenuse, which is this right here. Got it? So this line right there is Z. And so Z is the impedance, which is the total opposition to current flow, just like resistance is in a DC circuit. Z is like R total for DC, but it's not. It's something different. So now I got Z. Well, where in the heck am I going to get Z? How am I going to figure out what that is? I bet there's a formula, but you already know it because I just heard it back there. Pythagorean's theorem, which is what? Okay, so to find Z, so the Pythagorean theorem, oops, spell it right, Pythagorean theory or theorem, says a square plus b square equals c square. All right. Well, a lot of good that does me because I don't see a, b, or c up there. How about x total plus r total squared equals z squared. The same thing, I'm going to write it just a little bit different. Z equals the square root of r squared plus x total squared. Huh?
R squared.
Oops, sorry.
R2.
Or z equals the square root of r, I'll do it right, squared plus x of L minus x of C squared. What I did is I just took this right here and expanded it out, because x total is x of L minus x of C. All right, so these are the same formula. So you're going to want this formula or this formula. I'm going to kind of do it my way. I'll show you how I like to do it. So, let's figure it out. What is z in this case?
10.
Is it 10? Okay, so z equals the square root of r squared, so that's 8 squared, and I can use this one over here because I solve for xt, plus 6 squared. Now, I didn't bring my calculator in, so
64 plus 36.
what do we got?
100.
8 squared?
100.
8 squared is not 10.
No, it's 64 plus
Plus 6 squared.
36.
So we're going to square equals the square root of
100.
100, and the square root of 100 equals
10.
10. Look at that. So 10. What is 10?
Z.
Z equals 10. That is my impedance.
Kevin,
Yeah,
what if
that would never happen. Don't even ask.
the given number of xc is given as a negative?
Oh, what a wonderful question. Let's just turn this around just a little bit, and let's just say that, I'll put it over here in blue. Let's just say that x of L was 4 and x of C equals 10. Right? Then x total equals what? So it's the formula.
6.
Here's the formula. X total equals x of L plus negative x of C. So in your calculator, I would put 4 plus negative 10 equals
Negative 6.
negative 6. So then what happens is I go this way. 2, 4, 6. So it becomes here,
The same.
and it goes that way.
It will be the same.
Now, the funny thing is, Z is going to be the same length.
Yeah.
Because just because I used the same numbers. So it came down 6 here as versus up 6. It's the same. Now there's an angle
Square of.
that is created right here, this angle between R and Z. That's an important angle. All right? And so I want you to imagine if back there, if Harold is doing his job really well, and x of L and x of C are the same, then what is xt? We got all kinds of inductors running off, and I've got x of L of 100, but Harold's doing his job. Got a cigar. And he puts on just the right amount of capacitors, so x of C equals 100. Then what is x total? Let's hear it. 0. So 100 minus 100 is? 0. So that would put me right here on this line, wouldn't it? And so this would be my,
Resistance.
and then there's the resistance. So what does the Z line look like?
Same like.
Well, then it's going to be right here. There's Z. Is that good or bad?
Good.
And what is the angle between R and Z?
0.
That's a 0 angle. That's my phase angle. That's good. That's what I want, right?
Yes.
Okay, but let's go back here. In my example, here's my angle between R and Z. That is not 0. That's bad. And this angle represents how far off phase angle we are.
Is that in degrees?
It's in degrees.
So the z angle, do we find the z, which is 10 degrees?
No, you found the Z, which is a length of 10. The length of 10 then is that. Now we got to find that angle.
What units is Z in?
Ohms.
Ohms.
All right. Everybody with me so far? So Z gives the total resistance. I'll write that. Z impedance gives the total resistance R plus C plus L to current flow. All right, point G, because I don't know. The position, and by that I mean the angle of Z is the angular distance, or difference between voltage and current. Phase angle, that's the phase angle, we know what that is, right? Is represented by the Greek letter theta. Which is kind of a zero with a line through it. Okay, so what have we figured out so far? In a purely resistive circuit, the angle of theta is how many degrees? 0 degrees. That's a good thing. In a purely C, the angle of theta is going to be crickets.
Negative.
Okay, I'm going to draw it right over here. Here's my thing that I drew. Here's x of L is here, x of C is here. What happens if my Z is going right down like that?
Negative 180.
So how many degrees out am I?
90.
90 degrees. 90 degrees down. So in a purely inductive circuit, what's my angle?
Plus 90.
In a purely inductive circuit, the angle of theta is equal to,
Plus 90.
come on,
Plus 90 degrees.
90 degrees
Up.
up. It's going to go right here. Is that good or bad? Oh, it's not. That's not good at all. All right, so we got to compute that angle. How are we going to compute that angle? Oh, that was a bad thing. What were you doing while I was talking?
Catching up.
All right, to compute the phase shift in a circuit that is not pure, in other words, if we have a Z that is either not perfectly on the R line, perfectly straight up, or perfectly straight down, we're going to use trigonometric functions to figure this out.
But even if it wasn't perfectly straight up or down, you'd still want to verify that it was.
Yes, yes.
What does it say in yellow? 90 down?
90 down, yeah.
We need
So
find
will
some
X
midpoints.
And that's
will
90
always
degrees
be
up
on
and
top
90
and
degrees down.
XC will always be in the bottom?
Let's hang on. I'm going to pause this so you guys can get caught up.
Hey.
All right. It's all right. I want to look. I don't love where my notes are right now, to be honest. So I struggled through this here, as I think I went a long way around something, and I want to not do that. Okay. So to find out the angle, we need to find an angle. So we're going to. It's always a right triangle, which means that we have 90 degrees there, and so we need to find this angle right here. All right. So to do that, we're going to use trigonometric functions. And so we talked a little bit about this, I think, earlier in the semester. So we have something called sine, cosine, don't get ahead of me, and tangent. Tangent. And there was a mnemonic, is that the word, called Sohcahtoa, but I can never remember it because it's Sohcahtoa. Because if I had to pronounce Sohcahtoa, I'd be like, so, Sohcahtoa. And that doesn't help me at all. So I would not expect you to memorize that since I seem to fail at it. Sohcahtoa, which is another way of saying that sine of something is equal to the opposite, O, opposite, divided by h, the hypotenuse. And cosine is equal to A, which is the adjacent, divided by h hypotenuse. And tangent, tan, is equal to O, opposite, divided by A, which is adjacent. All right, and so if we're always going to be talking about this angle right here, right? This angle here. So this is always, no matter what, going to be the hypotenuse, because that just is. And when I'm referencing this spot, all the way over here is going to be the opposite, and all the way right here is going to be the adjacent. Now, you're going to come to a point where you're going to have to figure out this angle. But you're going to have the opposite, you're going to have the adjacent, and you're going to have the hypotenuse. Because the opposite is going to be what in terms of electricity? X total, okay? And the adjacent is going to be resistance. So opposite over here is going to be X total. It could be up and it could be down. I'm always going to draw it up, okay? X total. And the hypotenuse is always going to be Z. Now I'm just going to give you a little advice here. How did you get Z? What did you need before you got Z? Okay, you had to find XT, you had to find R, and then you had to do some math with X and R to come up with Z. All right, if you screw up on that math and you use Z to find this angle, guess what your angle is going to be? Wrong. So I never choose the one that has the hypotenuse. So I don't want to choose this one, and I don't want to choose this one. Why? Because it's just one more thing that could have gone wrong. So let's say you get x of t right, and you get r right, and you use tangent. Is your angle going to be right? Yes. What if your z is totally wrong? Doesn't. Then you missed one, but you still got the angle right. If you use either one of these that use the hypotenuse, not only did you get, and you get z wrong, you get z wrong and you get angle wrong. Just my advice. I don't care. So do it however you want. Okay. So let's just say, I hope this goes right. So if R equals 10 ohms and X of L equals 30 ohms and X of C equals 10 ohms, then what is X total? Hey, what is XT?
20.
Everybody should have got that because you have your formulas in front of you and you know that XT is X of L minus X of C, really, or plus a negative. So I have X of L is 30 minus 10 equals 20 ohms. Okay? Where does that go on my triangle here? Opposite. It goes right here. 20. What is down here on this line? 10. Okay, what is my z? Well, I don't really need to know right now, do I? If I just want to find this out. So let's try it. So, all right, so I'm using tangent, right? What is my opposite? So I'll write this here. Tangent equals opposite divided by adjacent. So that is equal to opposite. What's my opposite? 20 over 10, which equals 2. All right, I need my calculator. Oh, it's in my pocket. Look what I did.
No, you didn't have one, Kevin.
I thought I didn't either, Brett. Okay.
Why you lied to us like that?
63, 1, 40, 30.
Just liars, Kevin.
Okay. you have to make sure you get the order of operation correctly. So I have this particular calculator here. Now that I've gotten 2, well, so what? Is that my angle?
No, this is a tangent.
It's just 20 divided by 10, but 2 is the number I got to work with. In my calculator, I need not tangent, I need arctangent, which is tan minus 1. All right? Tangent is used to find the distance when you know the angles. Arctangent is used to find the angles when you know the distance. So here's what I'm going to do. I'm using tangent. So in my calculator, I'm going to put 20. Is that what I did?
Minus 10.
No, not minus 10. Divided by 10 equals, and I get 2.
2.
Okay, then I've got 2. I want to make sure it works on the 20 divided by 10 equals, and I get second tangent. Not on mine, I don't. Okay, then I have 2 in there, or I could just put a 2, and then I have to hit the second key, and then I have to hit the tan key. Why the second key? I want to hit the second key because above tan it says tan minus 1, and that's arctangent. Everybody follow? Okay, so 20 divided by 10 equals 2, because that's the opposite, 20, divided by 10, the adjacent. Everybody follow that? Okay, the division equals 2. What is the arctangent of 2? Arctangent of 2 is 63.43 degrees. So this is 63.43 degrees. Now, let's just for fun, because it is, let's try to use sine. So if I wanted to use sine, what do I need? Z. So I need z. So z is the square root of r squared plus xt. And I already got square. And I already got xt, which is right down here. So it's z equals the square root of 10 squared plus 20 squared. All right. So we do what's underneath the radical sign first. So 10 x squared plus 20x squared equals 500. So I'm not done yet though. So z equals the square root of 500. Now I'm just going to hit this little square root key. And what'd you get?
22.
So z equals 22.36. It's actually ohms, so z equals 22.36 ohms. Now I want to solve for this angle. But this time I want to use sine. So it's getting a little messy, sorry. So it's opposite. What is my opposite? 20. What is my hypotenuse? 22.36. So it's 20 divided by 22.36. So 20 divided by 22.36 equals 0.894 something. I'm going to hit second sine. And I get, thank God, 63.43 degrees. That number sounds vaguely familiar. We got it right there.
So that's you can just do it again and recheck if your z is correct.
Yeah, you can even use that to check your z to make sure it was correct. Good point. All right, don't go away mad, don't go away afraid. We will do more of these tomorrow.